Welcome chemistry students, I'm Mrs. Gregory. I'm going to talk to you today about part 3 of our arrangement of electrons in atoms chapter. This is the first half of the chapter, yet part 3. You've heard from Ms. Rashar in part 2 and Mr. Suston in part 1. And what I get to tell you about today is kind of the nitty-gritty of how these equations and things for describing electrons came about. So you know about the Bohr model of the atom, and you know that that's the one with the nucleus in the center, like Rutherford had told us, and electrons in energy levels or rings around the nucleus. Okay, now we also know that from the signals we get from the atom, all those pretty colors we see in flame tests and through spectroscopy through the gas emissions tubes, that those electrons can get excited by energy and they can move to other levels. Well, Niels Bohr, as he studied hydrogen, actually figured out how much energy it would take to excite a mole of electrons of hydrogen so much that they didn't just jump up to higher levels, they actually jumped up so far that they left the atom altogether. That's really exciting. So he figured out that that is 313.6 kilocalories of energy per mole. All right? Now that just works for hydrogen. The fact that this is done per mole is important because he couldn't study just one atom of hydrogen. And the fact that this equation involves the energy level, that n squared at the bottom of the equation, that means the energy level. It allows us to calculate the energy changes for the jumps of the hydrogen electron anywhere within the atom. It's telling us either how much energy has to be put in to excite the electron from a lower level to a higher one, or how much energy is released when the electron jumps from a high level back to a low one. And that negative sign on this equation sometimes confuses people, but it is there to tell us that if the electron came from outside the atom and fell down close to the nucleus of a hydrogen atom, 313.6 kilocalories per mole of energy would be released. We tend to use those values in joules now, that's the SI unit, but you do see this 313.6 kilocalorie value relating back to Bohr's original research. Okay, so this is all great in theory. It's a perfect example of science at work. It shows how we have refined the models of the atom even more, but it really only works for a very simple atom like hydrogen, where there's, in the model here, the diagram, there's one proton, there's one electron. We don't have to worry about electrons bumping into each other or coming close to each other. Is there an interaction there? Which happens in most of the elements, because most of the elements have more than one electron. So this model proved to be a little bit too simplistic, but it does do a lot to explain why we see those certain bands of color when we're looking at the spectra of various elements. So it's a good basis, a good foundation for our further study of the atom. Well, who helped fix that? Louis de Broglie. He's a French scientist. He actually combined the work of two very prominent physicists, Albert Einstein and Max Planck. You heard about him in the previous screencast. And de Broglie put together the equations, the famous E equals mc squared, and then Planck's E equals hf, where the energy of the electron is Planck's constant times frequency, merged those two things together and came up with this idea that, you know, electrons must be behaving like both waves and particles, kind of this dual nature of peace, love, and harmony that allows us to describe electrons and what they're doing in atoms a little bit more clearly, even though it might not seem too clear to you guys right now. So if electrons, which are little tiny particles, can behave or move in a wave pattern, that explains why they can fill up the space of the atom. It explains something about the energy signals that we get from the atom, and it just makes a little more sense when we think about the fact that those electrons are so tiny compared to the nucleus of the atom, for instance. Wow, look at that fancy schmancy equation. Okay, here's another famous physicist, and a little heads up for those of you that go on to study chemistry in college, probably your third year of chemistry and physical chemistry, that's when I had it anyway, you'd have to derive that equation on perhaps one of your tests. That is the Schrödinger wave equation. Okay, so you're thinking, wow, who would want to do that. But you never know. You might find yourself in a chemistry career. Okay, so now that we're trying to describe this motion and behavior of electrons, we have to consider something else. And our scientist friend Werner Heisenberg came up with this Heisenberg uncertainty principle, telling us we can't know exactly the location and the momentum of an electron at the same time. We can get some information about one of those factors or the other, but for instance, if an electron's moving, then we can't tell its location. If its location is known, then it's not moving. So we can't know both of those at once, and yet we still have this idea that electrons are moving so incredibly fast in an atom. So both of these factors have to be considered at once. Here's a beautiful picture of a hummingbird. Okay, if you've had the pleasure of sitting and watching a hummingbird fly around, you know that hummingbirds can fly in all sorts of different directions. They don't have to just fly around in circles around the feeder. They can fly up, down, sideways, kind of like little helicopters. And when you watch a hummingbird moving, its wings are flapping incredibly quickly. We can't see the wings there because they're moving so fast, but we know they're in there. We know probably where they're going to be, and that is kind of a rough analogy, but very similar to the kind of thinking you need to do when it comes to describing the location and momentum of electrons in atoms as well. Okay, here's Erwin, the Schrödinger equation. We're not satisfied in science to just go along with explanations from people even as smart as they are, like Albert Einstein, but we want to find a mathematical basis for this. Is there a mathematical way to explain the motion of electrons? Well, the Schrödinger wave equation did that. It verified the Heisenberg uncertainty principle. Basically, that big long equation describes electrons moving in a wave pattern, and it essentially says the electron's here, now it's 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 here, approximating the location of an electron and its momentum as well. So it's great that we could get this mathematical basis for this. It lends credence to our understanding and explanation of the atom, and even though it might make things a little bit confusing right now, it is a great thing to fall back on when we're trying to describe something so incredibly tiny like the electron. This led to a new form of physics called quantum physics or quantum mechanics. Classical mechanics describes motions of big things like cars and baseballs and so on. Quantum mechanics describes these tiny, tiny, tiny electrons moving at speeds, beyond our comprehension sometimes. And it allows us to develop a theory, remember that's an explanation, that this space around the nucleus, this electron cloud, is an area where it's highly probable or highly likely to find an electron in an atom. We can't tell exactly where it is within that cloud, but we know there are certain areas where that electron is going to tend to be. Those areas are called orbitals. And I usually use this analogy in my class. Imagine, during a normal school day, we could take the roof off of the school building and peer down inside at all the happy students and teachers working throughout the school day. We would see people in classrooms. We would tend to see people in classrooms. The bell would ring. People would move around to other areas. They're free to move around, but they tend to end up in classrooms throughout a normal school day. Similarly, there are places within the atom where the electron tends to be, and they like to be closer to the nucleus. They're drawn to the nucleus because of the opposite charge attracting, but sometimes they can be further away from the nucleus as well. So keeping in mind this idea of probability as we go on into the second half of the chapter, where we'll describe a little more carefully where the electrons are when the atom is in its ground state, its not excited state. Okay, here's another example. Beautiful field of sunflowers, and in the middle there is a beekeeper. Well, if there's a beekeeper in this field of sunflowers, you can be assured that there are bees. There are bees somewhere. We can't see them in this picture, but we know they're there. And if we could step closer in this field of view, closer to the beekeeper, we're going to find more bees because the bees are going to go towards their hive. They're attracted to their hive. Way off there in the horizon, there are still bees, but probably not as many. They tend to be closer to the hive. electrons tend to be closer to the nucleus of an atom because of that attraction. And we could probably calculate a probability of finding bees in this field of sunflowers if we really wanted to do that as well. So thank you for watching this third part of the first half of our chapter notes. Please remember to watch the other parts as well. You might want to even jot down some notes for yourself. And happy studying!